Welcome to the fourth module in the course on environmental geography. This is the chapter based on geosphere materials, and I'm Nathan Bowden, your instructor for this course. In this module, you will learn the chemical composition of the geosphere, what minerals are and how they are made, the physical properties of minerals and their uses, how minerals change, which is also called the rock cycle, how rocks form and change, uses for rocks. Rocks are the most common geosphere material, and we humans use them for many things, such as entertainment or for art and to build things. Rocks can be very useful, as shown here in the two photos. On the left you see a rock climber, and on the right you see a statue. The geosphere, of course, has a chemical composition made up of elements. The smallest substance that cannot be broken down any further is an element. 8 elements make up more than 98% of the geosphere's mass. I believe it's 98.2% of the total geosphere's mass is composed of 8 elements, and we will be looking at those shortly. Atoms, a short review on what atoms are. Atoms are the basic building block of all things, including minerals. And minerals are the building blocks of rocks. Atoms can be divided into 2 parts: the nucleus, where the positively charged proton and the neutral charged neutron reside, and the electron, which is on the outside in different shells and different levels outside the nucleus. And this is where the negatively charged electrons are located. The composition of the geosphere. The crust we have directly observed and sampled. This is what we walk around on, mountains made from, etc. But the composition of the deep earth, the mantle and the core, is only known from the density of the earth through density variations from seismic velocities, the composition of meteorites which have fallen to the earth, which you have studied, and the assumptions of the formation of the solar system. This was discussed in the second and third modules. As I mentioned, there are 8 elements which compose 98.2% of the geosphere. And here you see on the left-hand side the chemical makeup of the geosphere in numbers. So if we were to count them, 32.1% of the elements would be iron, 30.1% would be oxygen, 15.1% would be the element silicon, and oxygen and silicon is these two elements forming a compound are very prodigious in the geosphere. Magnesium is 13.9%, sulfur at 2.9%, nickel 1.8%, calcium 1.5%, aluminum 1.4%, and all other elements are only composed 1.8% of the geosphere. In the right-hand side, in graph B, we see the percent composition by mass. So in the first figure, we looked at, if we just counted them by numbers, and on the right hand, looking at the mass. Oxygen being a rather heavy element by mass, it of course is percent quite high. Here we see the difference between the blue bar, this oceanic crust, which is underwater, and the brown continental crust, which is land. As you see, there's slightly more oxygen in the continental crust than the oceanic crust. Silicon is much higher in the continental crust than the oceanic crust. Aluminum slightly higher than continental to oceanic. Iron in the oceanic crust is higher, partly because of, as you remember, the depth. Iron is somewhat dense, and so it will be lower in the crust, and also that there's a very high composition of the core of the Earth is made of iron. Magnesium is more prevalent in the oceanic crust and the continental crust. Calcium, much more, almost twice as much. Sodium is more prevalent in the continental, and potassium is the same. So the difference is, and just a few short points, between continental and oceanic crust are the combined percentage of iron and magnesium in the oceanic crust is 60% greater than the continental crust. So these dense elements are more prevalent in the oceanic crust. The percentage of calcium in the oceanic crust is nearly twice that in the continental crust. The percentage of potassium in the continental crust is 15 times that in the oceanic crust. And going back to calcium, we will discuss a little bit later why it's much higher in the ocean. Potassium is in the continental crust much higher. And silicon in the continental crust is 20% greater than the oceanic crust. Again, a quick review of chemistry before we go on about the bonding of the elements and how they form minerals and how minerals form rocks. There are two basic types of bonds. On the left-hand side in figure A, you see the ionic bond. An ionic bond is the transfer of an electron from the outer shell of one element to another element. A very commonly used example of this is sodium chloride or salt. In the top, you see sodium has only single electron on the outermost shell, which is very unstable, and the chlorine has 7. Because of the octet rule, octet coming from the Latin of 8, 8 is the norm for an outer shell. So it wants one more. It has 7 and it wants an 8th. So what happens? The sodium gives off its outer shell electron, so that its outer shell now has 8. And the one single is gone and transferred to chloride. Chloride now also has 8 in its outer shell. Because it has one more electron than protons, electron being negatively charged, proton positively charged, we see that the chloride atom is now negatively charged. So I repeat, it has one extra electron more than protons. The opposite is now said of the sodium. It has given off an electron, so it now has one more proton than, which is positively charged, than negatively charged electrons. So it has a positive charge. The difference between an ionic bond and a covalent bond, on the right-hand side you see an example of an oxygen atom and 2 hydrogen atoms. In a covalent bond, the elements cooperate in the covalent bond, which is how you can remember that, covalent, cooperate, in which the electron on the outer shell of oxygen is shared with hydrogen, in this form forming water, H2O. Common rock-forming minerals in the geosphere, which are composed of elements: quartz, feldspar, ferromagnesian minerals, and each is identified by a unique combination of physical and chemical properties, namely composition, color, luster, and hardness. Now these are the minerals which will later compose rocks. But first look at the building materials, minerals. Oh, and density. A big difference between a rock and an element. Here we have 2 forms of carbon, but in different crystal forms. On the left is a diamond, which is a pyramidal structure. Both are made of covalent bonds. On the right you see graphite. Both diamonds and graphite are made purely out of carbon. They all have only covalent bonds. However, the pyramidal structure of the diamond has a very strong force, and the sheet formation of graphite is a very very weak force. So diamond is hard on the Mohs scale of hardness and is commonly translucent. You can see through it. However, graphite is soft, so it'll have a low number on the Mohs scale of hardness, and it's flaky and dark. Quartz is a combination of silicon and oxygen, as I mentioned before, the second and third most common elements on the geosphere. This is a tetrahedron structure. That means that there is a small silicon, there's a small element, silicon, surrounded by 4 oxygen molecules and a 4-sided pyramid structure. It's a tetrahedron. These tetrahedrons can form into chains, as you see in C, which are just tetrahedrons upon tetrahedrons. So the carbon-carbon bond, a double chain, and lastly, a sheet. Quartz is slightly different. Quartz is 2 oxygens and 1 silicon. It is most often clear, white, gray, sometimes rose-colored and smoky. It's approximately 7 on the Mohs scale of hardness, which is pretty hard. It's a 6-sided prism, as you see in A, figure A. It has a conchoidal fracture. It is not chemically reactive. Some environmental health and risk. So quartz can form very tiny particles and enter your lungs. The particles get stuck in the opening of your lungs. They cause inflammation, and these inflammation can cause nodular lesions in your lungs. Your lungs will therefore deteriorate. This causes shortness of breath and fever, and this is the scientific name for this is called silicosis. Silicosis has an even longer scientific name, pneumono-ultramicroscopic silicovolcanoconiosis, and this was very common in a mine called Hawk's Nest in West Virginia, where it was first, discovered. It was first written down as a disease from miners. Another form of rock being formed by quartz is granite. But here you see the Mount Rushmore carvings of granite. Granite is an aggregate. I'll talk about different types of rocks, but as a aggregate of different minerals, namely quartz, potassium feldspar, which we'll be talking in the next slide, where that is, plagioclase feldspar, and biotite. Feldspars are different than quartz that we saw previously. They are examples of them are potassium-rich feldspar, which is potassium and aluminum, as well as the silica and oxygen. Plagioclase can either have sodium or calcium, as well as the silicon. They are white, gray, pinkish. They are on a 6, which is an average of hardness from 1 to 10 on the Mohs scale. They form 4-sided prisms at cleavages of 90 degrees and have, just like quartz, a conchoidal fracture. Lastly, they crystallize over a wide range of temperatures, but still at temperatures higher than what we normally have on Earth. On the atmosphere. So, as I mentioned, feldspars form at higher temperatures than we have on a stable Earth atmosphere, and also where we have lower pressure than under the crust. So, normally formed under the crust, and when it is exposed to the atmosphere, it will become weathered. There are different types of weathering. You have chemical and physical weathering, examples of which are hydrolysis, which is a reaction of water with minerals to form new minerals. Hydro being water and hydrogen, and lysis is splitting. And dissolution, which is a chemical atomic constituents being dissolved and removed. Feldspars are very common in our Earth because they form. On the left you see clay. Clay is not a very stable structure, and if you were to build a road on clay, like in the picture on the left, you'll see that it will compact. They also form micas, which are silicate materials, which are planar, which cleave into sheets. Here we see a couple of examples, one of which is biotite, which is very dark mica, and it has iron, which causes it to be dark, and muscovite, which is more silvery, and it's very potassium rich. Different types of ferromagnesian minerals, and it's called ferromagnesium because they use either iron, the ferromagnesium, or magnesium in the mineral structure. Both are +2 charges. They both have given off 2 electrons from their outer shells, and so they're interchangeable. Some examples are olivine, which has 2 of either magnesium or iron, plus SiO4, which you can remember is quartz, which is greenish, about level 6, and conchoidal fracture. That you see that in photo A. And pyroxene, photo B, which is Se2O6 with either magnesium or ferric elements, or calcium in this case. Again, a Mohs scale of 6, hardness of 6, and it's quite dense. It is not a conchoidal fracture, it has 2 cleavages at 90 degrees. Ferromagnesian minerals can be dangerous, as you see on the left as well on the right. They hydrolyze and form serpentine minerals, and these are elongated fibrous serpentine minerals. That means they're very fibrous. They are the principal mineral in asbestos, and because of their heat-resistant qualities, they're quite flexible. These, again, if they get in your lungs, can cause quite a lot of damage. Ferromagnesian minerals, some more, include biotite, hornblende, and we'll go further on into sulfides, oxides, and carbonates. Here we have, you see a picture of pyrite, which is a sulfide, which contains a sulfur, which is a 2 charge. Different types of sulfide include galena, sphalerite, and pyrite, which is shown on the right. It's also called fool's gold. These are the sulfide minerals. They are concentrated into metal-rich deposits, and they are quite heavily mined. The processing of the minerals to extract the metals is an environmental issue. Going on to oxides, they are a combination with oxygen. We have here different types. Titanium oxide is called rutile, tin oxide, cassiterite, iron oxide, 2 of them, magnetite and hematite, and lastly goethite. Oxides are more stable, are less chemically reactive on the Earth's surface than other minerals. They commonly survive weathering, and like quartz, if you did not know this, are formed into sand. And several minerals react with oxygen. The positive ions combine with oxygen form oxygen minerals. This is called oxidation, and where an electron will transfer. And this we can see in rust, which is a combination of hematite and goethite. Oxidation also gives quite a lot of earth a rusty color, an orange-brown color. Carbonates are a combination of positively charged ions, so these charged positive ions are also called anions, so calcium, magnesium, iron, as well as negatively charged carbonates, CO3. So here is 2 examples, calcite and dolomite. These are rather soft minerals, on level 3 on Mohs scale, have cleavages often in 3 directions. These are called rhombs. They're prone to dissolve in acid, and they in landscapes they call karst terrains, which you'll see in the next slide, which is land that has which is specifically very calcite rich. Because it weathers through rain, these develop caves, sinkholes, and also disappearing streams. So here's karst. Karst, as I mentioned, is the dissolving of carbonate minerals underground or at the surface. They form the carbonate. If you go way back to the very beginning of the presentation I mentioned, we'll talk about why calcium is so rich in the seawater, specifically because of marine animals, which, as all animals, have calcium in them. When the animals die, they participate the minerals into the seawater, also making into shells and other structures. And when they die, they form calcium-rich structures. And when they die, they compact in a process called lithification, which we will discuss later. And lithification is making of stone from minerals. And a form of calcium carbonate is limestone. So in photo A, you see the Great Mammoth Cave in Kentucky, which is dissolved calcium carbonate under their surface, but they also can dissolve on the top of on the surface itself, forming hummocks. And lastly, if it's just under the surface, a very dangerous part is sinkholes, which is a sudden collapse of a near surface cave when it reaches a breaking point and comes crashing down the surface. Igneous rocks. So how rocks are formed? One form is igneous. Igneous rocks are formed from molten rock or magma. If it crystallizes, it solidifies in a crystalline form. It's either felsic, which is feldspar and silica, or mafic coming from the magnesium, the Ma from magnesium, iron. Felsic is more characteristic of continental crust, and mafic is more oceanic crust. You also have intrusive rocks, which come from the erupting and rapid crystallization of magma. These are basalt. And extrusive, which is a very slow cooling down, and this type of rock is called gabbro. Here we see the difference between basalt and gabbro. Basalt is in photo A, and here we see a 30 micron thick slice. It's made up of different types of rectangular crystals, such as feldspar. Variably, you also have olivine and pyroxene, and they are extremely small because of the very quick cooling of the lava, the magma upon explosion. The gabbro cools down much slower, so it has feldspar and dark crystals, feldspar and pyroxene, but because it cools down slower, the crystals are much larger and has a grainier, a coarser composition than basalt.
Igneous features. Magma intrudes from below to form a large magma chamber and smaller igneous intrusions. Some of the magma rises through conduits to form volcanoes at the surface. The solidified igneous rocks include dikes, which intrude across the sedimentary rock layers, and sills, which intrude between the layers. Erosion exposes the igneous rocks that solidified beneath the surface. Where erosion exposes plutonic igneous rocks, they are commonly more resistant to erosion than the surrounding rocks. This means that the plutonic rocks stand out on the landscape as hills, ridges, and even large mountains where softer enclosing rocks have eroded away. At this stage in the landscape history, a dike stands up as a long ridge, and volcanic necks represent the magma that solidified in former volcano conduits. Deeper erosion exposes the large magma chamber, called a batholith.
The ocean crust has different layers as well. First you have the sediments, followed by the basalt, which is from the lava flow. Under that you have sheeted basalt dikes, because the basalt will compress as it goes lower, higher pressure and higher temperature. Under that is the gabbro intrusion of these, that is the slowly cooling magma. And lastly, you have mafic rocks, mafic being magnesium rocks. The continental crust ranges from mafic in the lower to felsic in the upper. It's originally basaltic. Today, the oceanic crust is altered by hydrolysis with seawater. This recrystallizes during subduction, releasing water and melting the crust. This melting forms an intermediate magma, characteristic of subduction zones, and these are often explosive, such as volcanoes, and they release volatile gases, so H2O, CO2, H2S. That's water, carbon dioxide, and hydrogen sulfide. And andesite is intermediate mafic, as well as plagioclase minerals. The rock cycle, we can start off with melting under great temperature, going clockwise. This melting crystallizes, forming the igneous rocks, which we just discussed. The weathering and erosion causes then sediment deposition. The sediment deposition under pressure and temperature, this is called lithification, forms the rocks. It's called sedimentary rock. Sedimentary rock under even higher heat and pressure, which causes the minerals to recrystallize into new minerals, forms metamorphic rock. Again, these rocks of sedimentary rock and metamorphic rock can erode again, causing more sedimentation and again sediment or metamorphic rocks, or they can melt because of magma or just heat and pressure. Weathering, back to weathering, which we discussed just a little bit. Weathering is, again, as I mentioned, the physical and chemical process of changing rocks on Earth's surface. The rocks come up because of plate tectonics, as discussed previously in earlier modules, and come to Earth's surface. There is caused expansion. The break in the rocks is called a joint. You have physical weathering, the breaking of rocks through physical processes, either, for example, a frost wedge, so that's through the freezing and melting through the season. Water, H2O, goes into these joints, into the crack between the rock, and expand as it freezes and contracts as it warms into liquid. This causes a wedge. Over very long periods of time, these will crack the rock. Or root wedging, in which case a plant physically forms roots through the rock structure. Chemical weathering comes through the form of hydrolysis, that's oxidation, and dissolution, which we've all discussed previously, but to recapture that, hydrolysis is the breaking up of the rock through the presence of water. Oxidation is the transfer of an electron from an oxygen to an element, an example of this being rust. And dissolution, which is the dissolution of a single element in an mineral into the water structure.
Freeze and thaw. This animation shows how water, when frozen in the cracks of rocks, breaks down rock. Water expands when it freezes, and the expanding ice exerts sufficient force to break rock apart. Water enters rock along existing fractures and then moves along boundaries between mineral grains or into open spaces between minerals. When the water freezes, the expanding ice forms new cracks that provide new openings for more water to enter after the ice thaws. The close-up view shows how cracks deepen during repeated cycles of freezing and thawing. Eventually, the rock breaks apart. Salt weathering. This animation shows how, when salty water evaporates from cracks in the rock, it results in the growth of mineral crystals that forces the rock apart. Water enters rock along existing fractures and then moves along boundaries between mineral grains or into open spaces between minerals. When the water evaporates, the crystallizing salt minerals expand to produce more cracks that provide new openings for even more water to enter the rock. The close-up view shows how cracks are enlarged during repeated cycles of wetting and drying. Eventually, the rock crumbles apart.
Here we have some pictures of weathering process. In photo A, you see the frost wedging, cracks and disaggregates or breaks the rock. And B, you have root wedging, which is the growth of plants through the rock. And chemical weathering, such as hydrolysis, which causes decomposite rocks. Erosion is different than root wedging and frost is the transportation of materials through water, wind, or ice, such as glacier. This is a gravitational pull. Glaciers, as they move down a mountain, they scrape the material off the valleys and carry it down to debris. And debris from a glacier is called a moraine. But also streams and rivers are very common. A fast deep stream will carry and can move very large rocks called boulders. They will abrade and pluck material from valley walls. They will be rolled and bounced along the bottom. This is the bed load. And smaller sediments will also be suspended, smaller sediments being sand or clay. So clastic elements composed of different fragments of materials and chemical sediments are precipitation from solution. So we have these classic sediments which are transported mainly by moving water from the original source, deposited based on their size. The bigger the deposit, such as gravel, the farther it will be transported, and the smaller, such as silt, clay, or mud, will be transported very large distances. Here we see different photos. In A, you see a sediment transport from falling rocks in the steep terrain, and then within these valleys, in photo C, rivers are formed which carry the rocks and the clay and the sediments into photo B, to the coast. And the smaller rocks, the smaller sediment is carried further, so clay and silt. Here you see the clay and silt from the river on the coastline.
Sediment transport by streams. As the river current flows from left to right, notice that the sediment particles move in 3 different ways. The largest particles roll or slide along the stream bed in discontinuous movements. The smallest particles are completely suspended in the water and move with the current without touching the stream bed. Particles of intermediate size bounce along the stream bed. In most energetic streams, the large rolling and sliding grains are gravel, the bouncing grains are sand, and the suspended grains are silt and clay. Not visible in the water, but still important to remember, are the abundant ions and chemical compounds dissolved in the water. Watch the 3 different types of sediment transport motion: sliding and rolling on the bed, bouncing along the bed, and suspended above the bed. Bed load describes the sediment grains that spend most of the time on or near the bed. These are the sliding, rolling, and bouncing grains of gravel and sand. Suspended load is the fine-grained silt and clay particles that move within the stream current and rarely, if ever, settle to the stream bed. Dissolved load describes the ions and compounds dissolved within the water.
These sediments then aggregate together. As you see in photo A, so muddy sediment turns into shale. Shale is the aggregation of muddy sediments. Sandstone is the particle when the slightly larger particles of sand aggregate together, and gravel forms a conglomerate. So the largest particles together are called conglomerate. Sedimentary rocks they generally precipitate through evaporation, increase their concentration of seawater. So these are evaporites. Limestone is a very common chemical sediment, including calcium carbonate. So these are fossiliferous, oolitic, crystalline, or microcrystalline. And gyprock, which is some mineral gypsum, CaSO4. Lastly, we have rock salt. Limestone, quite often coming from the ocean because of the sedimentation and the precipitation of calcite on the seafloor, and these through marine organisms. And again, these organisms are lithified, and they form rock. Metamorphic rock is when these sedimentary rocks change through very high temperature or pressure. Any rock can be metamorphosed, so igneous as well as sedimentary, and even other metamorphic rock can be re-metamorphosed. The minerals which are formed at the surface are not stable at very high temperature and pressure. They recrystallize to form minerals stable at a higher temperature and pressure. Recrystallization largely involves dehydration, so the expression of the hydrogen molecule, and new minerals grow in different orientations. Typical metamorphic rocks include schist. It's a very flaky mica mineral, which are oriented parallel to each other, so they can form very thin layers which break laterally. Gneiss, which is discontinuous layers called lens of larger minerals, so quartz and feldspar, and separated by a finer grained schistose layer. So from an even higher temperature and pressure than the schists, and they can form from any rock, but especially from clastic sedimentary rock. And lastly, marble, which is a metamorphosed limestone. Here we see a difference between the schist and the gneiss. So the schist is very sedimentary, so shale, sandstone, crystals of that nature. And gneiss, which you see in photo B, has an even higher pressure and temperature. Rocks have several different uses, of course. Commercial and residential, so the building of buildings. highways, bridges, etc., cement, factories and power generation facilities, and also for water storage, filtration, delivery systems. Lastly, wastewater collection and treatment system. Aggregates, so that's sand, gravel, and crushed stone, which is also called common rock. We use that to make cement and asphalt. We spread this on our highways, our roadways, and building sites to stabilize the ground, because clay is not necessarily the best foundation. Our needs for aggregates are increasing because of our infrastructure. So you must think of bridges, highways, transit construction, roadways, etc. They are relatively cheap to mine and process, but very costly to transport. Here you see in the table below the amount of crushed stone which we are using through time, increasing dramatically. There, of course, are problems with aggregate mining, physical disturbances, because they must be removed. They form large pits, quarries, which are also remove natural vegetation. This, of course, can also be mitigated by having visibility barriers, slope contouring, so new soil and revegetation, reclamation, and aggregate pits can later be filled with water and form lakes and new wildlife habitats. Or again, can be transformed quite often into parks, gardens, and golf courses. However, they also causes a lot of dust, and not to mention noise. The breaking and the blasting and the hauling and the crushing causes this. The dust getting into our respiratory, the silicosis, as we mentioned before. Air quality must be monitored around mining areas. And of course, the noise in operation is a significant concern for anybody who lives near. Congestion and safety. That's the end of the fourth presentation for this module.